Hi everyone, welcome back to MATC58. We will be getting started by talking about linear difference equations. Before we get started though, I want to mention that I'll be making some definition and theorem references, and those will be to a textbook which I will link below and in the syllabus. We are going to be using as our primary text an Introduction to Mathematical Biology by Linda Allen, And occasionally, more so for the second half of this class than for the first half, but we'll also be supplementing with other resources, including the optional textbook, Nonlinear Dynamics and Chaos by Stephen Strogatz. I should note that Nonlinear Dynamics and Chaos is, in my opinion, one of the most readable math textbooks out there. It has some beautiful illustrations and is really good at giving people a sense of the intuition of the subject matter and not just the definitions and theorems or computations. However, it doesn't cover quite all the topics we want to talk about in this course, and so our primary text and the one we'll be following pretty closely will be Linda Allen's textbook. So, let's go ahead and get started. Let's see, definition 1.1. What is a difference equation? So, a difference equation of order k, has the form f of x sub t plus k, x sub t plus k minus 1, all the way down to x sub t. And we also have a t variable is equal to 0, where t is from the natural numbers. So this is going to be, for the purposes of this class, we're going to include 0 in the natural numbers. But 0, 1, 2, and so on. Where each of our state variables, which we're going to call the xi's, those are all in the reals. T is a real number. Well, it's obviously a real number because it's a natural number. And f must depend on both x sub t plus k and x sub t. So now, if f doesn't actually depend on both x sub t plus k or x sub t, it's still a difference equation. It just isn't necessarily of order k anymore. So it might be of lower order because it doesn't actually have the dependency on x sub t and x sub t plus k. And so just as a note, I mentioned this offhand, but we also have that the x sub I are called the state variables. So this is the state of the system. So for example, if we have an example of some sort of population growth, say cicadas, and how many, one of the state variables might be the total number of cicadas in a generation. So that would be a state variable x sub I. And then maybe the total number of cicadas in the next generation would be x sub I plus 1. Okay, so now we've defined in general what a difference equation is, we can classify them a little bit. So what are some properties they can have? Some of these will be very familiar from differential equations because difference equations are really just the discrete analogs of differential equations. But let's cover it all again. So a difference equation is autonomous, if f does not, not h, does not explicitly depend on t. And we'll call it non-autonomous otherwise. Okay, so this is a general definition of a difference equation. Often we'll encounter them in an easier to parse form. So let's write out one of the more commonly encountered forms. Which will be x sub t plus k plus some summation over I from 1 to k of a function a sub I which is a function of x sub t plus k minus 1, x sub t plus k minus 2, all the way down to x sub t, and of course it's also maybe dependent on t itself, times x sub t plus k minus I, which is equal to b sub t. So the b sub t layer is obviously only dependent on t, and it can't be dependent on any of these state variables. So here, what do we need? We have that t, again, is a natural number, and we know that this function, taking the functions a sub I, t plus minus 1 through x sub t and t, so that takes values into the reals, in the reals. And of course, b sub t also needs to be a real number. And the order of lists, order is k if a sub k is not equal to 0. So when we write out our difference equation in this form, it's relatively easy to determine whether or not the order is actually of order k. Okay, so let's see, definition 1.2. There are a particular subclasses of like differential equations. We care especially about linear and linear difference equations, and we'll be focusing on those mostly in this the first chapter or two of this course before we move on to nonlinear difference equations. So a difference equation is called linear if it can be written in a special form. Equation that can be written as x sub t plus k plus some summation from I equal 1 to k of ai sub, where each of our ai functions is only a function of t, xt plus k minus I, is equal to bt. So let's call this is now called linear. Otherwise it's nonlinear. So basically, the dependence on the lower order state variables can only come in this form, in this linear fashion. It enters into the equation, and it can't enter into our coefficient functions a sub I. And furthermore, if our difference equation is linear, so if a difference equation is linear, and we have that b of t is equal to 0 for all t in the natural numbers, then it is homogeneous. So this would be very familiar from your differential equations class. And otherwise, well, it is non-homogeneous. Note that we are only defining homogeneous versus non-homogeneous in the context of linear difference equations. We are not going to discuss what it might or might not mean for a nonlinear difference equation to be homogeneous or non-homogeneous. Okay, so now we have all that set up, we can also, so that's just a single difference equation. We can also talk about systems of difference equations. For reasons that will become obvious later, we're only going to talk about systems of first-order difference equations, since it turns out we can convert higher-order difference equations into systems of first-order ones, and so a system of higher-order difference equations can still be converted into a system of first-order ones. So, definition 1.3, a system of k first-order difference equations can be written as x sub I of t plus 1 is equal to f sub I of, so some function of x1 of t through xk of t, and t, so it's a function of t as well, for I equal 1 through k. And if xi of t plus 1 is equal to fi of x1 of t all the way through xk of t, So note that here the subscripts are no longer denoting time. The subscripts are denoting different state variables that are each evolving with time. Let's see, for all I in 1 through k, when it is autonomous. Because you note that we wrote out the dependence on t here. So autonomous and otherwise non-autonomous. Non-autonomous. And we still have the same sort of ideas of linearity and homogeneity. So if we have that x sub I of t plus 1 is equal to the summation from j equal 1 to k of aij of t, xj of t, plus bi of t, for I equal 1 through k, when it is linear. So you notice that the linear, that in this particular formation, instead of just having an arbitrary f function that can do crazy things with our state variables x1 through xk, the dependence on the various other state variables can only enter in through this linear summation term that we have here. So that's linear, and it's obviously nonlinear if you can't write it in that form. And if in addition, so if in addition to being linear, we have that bi of t is identically 0 for all I, of course, when it is homogeneous. And, well, now that we've defined what a difference equation or a system of difference equations are, we can also define a solution. So that is what you'd expect it to be. So this is definition 1.4. A solution to a difference equation, is a function. I'm going to call the function x from the natural numbers to the reals. That makes the difference equation true. The difference equation true. So basically, you substitute x in, x sub 1, x sub 2, etc., and the difference equation is true for all x sub i's. And we have something similar for a solution to a system of difference equations. So a solution to a system of difference equations is a function x from the natural numbers cross the set from 1 to k to r. That makes all the difference equations true. Equations true. Oh, I forgot to write in difference equations there. True. Equations. Okay, and often, so this is a sort of really mathy way of writing it, but often we'll write it in a slightly easier to parse way. Often we write a vector x of t is equal to x1 of t through xk of t. Transpose, since normally we prefer working with column vectors, since later on we'll see that there is a linear algebraic interpretation of all this for the solution. Okay, so one other thing about this course is that I will be going through all the material twice. So the first time, as we just went through, I'll be going through and giving the definitions and some of the more formal proofs. And in the next video, I will be going through the same exact material using the same text and going through and adding some more examples and intuition in case it's not clear. Because although eventually, as you move on further in mathematics, you'll be expected to be able to extract those insights from just the definitions and equations I've written down, it's often super helpful to have more examples and a careful walkthrough of the meaning of the proofs and derivations that I do. So that will be in the next video. I will see you there.